litho, like SML, a lot of all the processing tool, a lot of like long research, KOA, technical, they are all like Western company from Western countries. Right? So once like the United States say, okay, you cannot sell this to China, then China they'll stock in the maybe 40 nanometer technology node. It's even difficult to get into 28 nanometer. So that's the goal right now. They try to reach 28 nanometer technology node in China, right? But who knows? Maybe after 10 years, they will come out with some company, local company that can build the machine. But for the tools, like designing tools, like those CAD tools, I think that will be more, I don't know. Yeah. Okay. Okay, so what should we consider in the lithography process? Okay, the first one, resolution, which means how small can you make the device. You want to be smaller, the better, right? Because we continue the more slow, we want to reduce the feature size. And also the exposure field. Because our chip size will increase, just that we follow more slow, right? The small device, we increase the chip size. So the area or the field that you can expose at one time, that will affect your throughput. So you want to increase your exposure field. And also the alignment, the accuracy between this mask and next mask, placement accuracy is very important. And also the economy issues, the throughput. Like for example, E-beam lithography has the issue of throughput. Although it can give you a very precise, very small feature size, the throughput is the issue. Okay. Also the EUV, if you compare to the conventional like Simon lasers, I think the throughput is also the issue that will cost you more money and time. Right? And the last but not least, your defect density. Okay. As we just mentioned, defect is very important. That will affect your yield loss and also the cost. Okay. So that's the roadmap regarding the lithography technology. So what we just mentioned, they are all listed in the roadmap, like your CD, critical dimension, overlay, field size, and what kind of exposure technology. Okay. And this is more updated roadmap for lithography. Like you have UV and mask, also the DSA. Okay, so I think we won't cover EUV or DSA in this class. That's more advanced technologies. But we have to know the fundamental first. Okay, so we have seen these figures in chapter 1. The lithography just give you a basic idea how it works. Okay, so we have a film, we have a photoresist, and we have a mask, we have UV light, and that UV light will shine on your photoresist, and some of the light, some light are blocked by this metal on your mask. So that creates the pattern. You transfer the pattern from mask to photoresist. and then you use this photoresist to do the following process, either etching or metal. And once you finish the following process, you can remove this photoresist. Okay, so that's the whole basic litho process. Okay, so first, so we will introduce the photoresist, and we will introduce the how can we understand this photoresist developer and what kind of litho tools that we used in our fabrication process. So first we have to apply photoresist on top of your substrate. Okay, so after we clean and dehydration baking, which will dry out those water vapors on your surface of your wafers, then you can prime with HMDS. Okay, this HMDS is we commonly use that before we apply the photoresist, because it helps us to it's an adhesion promoter. So before we really put on our photoresist, we have to spin coating the HMDS first, because that will increase the adhesion between your photoresist and your wafers. Okay, so we can use these things. The photoresist are liquid, so you can spin coat it and spread it on top of your wafer. Okay, so if you want a thinner photoresist, you can spin this with higher RPM, like a spin speed. Okay, so here just some figures and description about how HMDS can help you to promote the adhesion between your wafers and photoresist. Because the silicon wafer is typically hydrophilic due to absorption of some water from the ambient environment. And in order to have your photoresist on top of it, the surface need to be more hydrophobic. So we have to dry out the water vapor first, and also we can use some HMDS film to make it like water repellent, and then easier for your photoresist to form a bond on top of your surface. Okay, so once we have your photoresist on your surface, then we can do following process, like you can deposit or etching or like make-off. Okay, so here I want to introduce litho process first. So for example, if you want to have metal at this area, then we have photoresist developed with this pattern, and they will deposit metal on top of it. So some metals will be deposited on top of your photoresist. And so once we develop it, we can remove this photoresist and also remove the metal. So we have metal left on a certain area that we want. So that's the litho process. Okay, but during this process, there's a possibility that we have metal coated at the side wall of your photoresist, and you can connect the metal together like this. So once you do the litho process, we develop this, sometimes this metal, because there's a connection from top to the bottom metals, because the metal also deposit on the side wall. If you remove the photoresist, sometimes this metal can be removed as well, right? Or if they stick here, you will see there's a rapid here, like this. Because that's the residue from the metal, from your metal deposition on the side wall. So that's we call some rapid here. Then if you have, for example, if you have like dielectric field deposition just come after this metallization, sometimes this metal spike will cause some short issues. Okay, so we will have a better way to do that is we can use a double layer photoresist to do that, because once we do the litho and development, we can create this undercut. Okay, we call this undercut. This undercut can prevent this rapid yield from happening, because your metal now first is you won't see this to connect because there's a gap in between, right? So when you have to do the label, then okay, you have a better idea. Okay, because the shape pattern is better. Okay, that's what we call it a bilayer or double layer process. Okay, that's the label process. But in our silicon IC fabrication, we seldom use label process. If we want a metal, we can just deposit the metal, and we can, for example, in this case, if we want metal remains in this region, we can use photoresist here, and we can etch away the metal that we don't want, and then we remove the photoresist. So this creates the same pattern as here. So this etch process is more common in our silicon process, in our silicon foundry, instead of label process. Right? But in some compound materials, compound IC process, they still use label process. Okay, so there's different purpose. Because for silicon, sometimes we have to control the critical dimensions. So using dry etching process is more easy for us to do this. For some other compound device, the feature size usually is larger, like even like sub-micron, like 100 nanometers. So we still can use level to do this. Okay, so I think we can stop here, and then we will continue this Saturday.